Swayam Prabha. Digital India. Educated India.
Today we will be discussing on one of the most popular ground improvement techniques, the use of preloading and vertical drains in the area of ground improvement, particularly when you are concerned with soft soils. The soft soils are particularly highly compressible, and most of them they are normally consolidated, or their over consolidation ratio is very low, in the sense that it could be 1.3 or 1.5 or 2, less than 2, where you have high elastic plus plastic deformations, and then the soils could exist even whatever, maybe 5 meters depth or 10 meters depth or infinite depth. The moment you load these soils because of the buildings and highway embankments, you end up having a lot of settlements. Bearing capacity of the soil is very low, and how do you handle this particular problem in soft soils is something that we will be discussing today. In fact, all the east coast and west coast of India and many places, they all have soft soils. Say for example, right from Calcutta to Visakhapatnam to the tip of whole of Tamil Nadu, east coast and west coast, and also Kandla, many places you have soft soils, and you have a lot of settlements. Many of them you have port structures here, and they have been using some of these techniques. Some of them are not new. They have been using this pre-compression and vertical drains more than 20 years, and we will just see how they are useful today in this particular lecture. This use of pre-compression or preloading has resulted in a number of techniques which have been used in the field. Actually, as I just said, some of the soils are normally consolidated. So, if you pre-compress, or like you apply the higher load such that the settlements are going to be less, it is called preloading. So, what we do in this technique is that we apply a higher stress than what is the stress that is likely to come on the soil, so that the settlements are preempted. Like we accelerate the process of settlements by using preload, and once you construct the structure, you will not have much settlements. So, that is what we say, it is called pre-compression or preloading. Then in this case of pre-compression, the consolidation of the soil in the vertical direction, say for example, if you apply load, consolidation occurs, and then the consolidation process results in the settlement. So, the acceleration of the settlements is because of vertical loading, and that is okay to some extent, but when the soils are of high compressible nature, you need to provide sand drains also. Actually, the sand drains, what they do is that they will also provide radial consolidation. So, you have consolidation in the vertical direction, and then the water is also coming out in the horizontal direction or radial direction. So, we call them as sand drains, and so the process of combining both vertical consolidation and radial consolidation has been initiated with sand drains in 1930s in the beginning. The moment people they had some idea of the consolidation behavior, they were able to understand that yes, if you are able to apply some sort of consolidation in the radial direction also, it is helpful. So, in fact, I will give you a classical example. If you are trying to do a triaxial test and a consolidation in a triaxial test and a clay, you put filter papers at the top and bottom, and also you surround the sample with some sort of filter paper where you have all the vertical drains, like we call there. Now, you can actually, you will see that if you do a consolidation test, there is a big difference in the way, the consolidation process itself, like it could be 3 or 4 times. You must have, I do not know if you have observed, but the fact is that if you have radial consolidation alone, it is one thing. I mean, vertical consolidation alone, it is one thing, but if you have radial consolidation together, then there is an excellent combination. So, you have sand drains, and since sand drains were somewhat, the thing is that was people were using in the olden days, but now you have what is called prefabricated vertical drains. Like you can see that you have a prefabricated vertical drains which are like these are all called prefabricated vertical drains, in which you have a say the if you put it in the soil, then this is called geotextile, and then this is a drain inside, you have a drain inside which has drainage channels. So, the moment you apply the load, water comes here and then goes to the drainage channels. So, this is one type here. There is another type here, like you can have a drainage medium here, like drainage channels here. Then you also have some more, like the top one is called drainage, the filter cloth, and this one is called drainage medium. And what we do is that earlier there was a circular sand drain which is about maybe 30 centimeters or 15 centimeters diameter, but then now you have this type of material where you have a consolidation which is quite fast using this technique. So, we will see that this is called prefabricated vertical drains, and you also have some more materials in the similar lines here, again some more, there are different companies. And actually what happens with these techniques is that the consolidation, instead of 8 to 9 years or maybe 4 or 5 years, it comes down to 9 months or 10 years, because you would like to accelerate the consolidation and construct at least next year. Like you go to coastal areas, what you should do is that within maybe you try to accelerate the consolidation in a period of 6 months to 1 year, then start highway construction next year. That is a normal plan. So, when these materials will help you to consolidate within 9 months to 1 year, then their purpose is served. So, there is no point in having this plastic material inside the ground when their purpose is served, and you have what is called jute geotextile. So, this jute geotextile is sufficient, and though this is biodegradable, it may last for 1.5 to 2 years, but then once you put like this, then the same purpose is served as that of this material. The difference is that this will not stay in the ground, but whereas this stays in the ground, and that way we can say that you are trying to provide a sort of a environmental friendly technologies using this sort of materials. And also in India you have, this is another one, this is called coir. This is again same coir which we normally know. So, both coir and geotextile are abundantly available in India, and people can develop some of these the prefabricated vertical drains and use it in the field, and they are maybe good for 9 months or to 1 year, but then we have seen that they have all the required properties which are comparable to the synthetic materials, and they are helpful. So, essentially we will be seeing some of these materials here. So, this is a typical example that I would be showing here. So, this is a clay soil which is about say 9 to 10 meters, then you have a fill. So, this is a typical example for a pre-compression. So, what we do is that we apply some sort of surcharge which is little, the total load is really higher, fill plus surcharge. They act on the clay soil, and you can see that if you just plot that settlement versus time, the settlement in the case of this clay without surcharge is like this, and then with surcharge it is like this. So, what we are trying to do is that in this process, like the settlement that is supposed to take place here, like it is you are trying to accelerate within some time, like because of the higher load it happens within this time, like this is nothing but the time for equivalent settlement with surcharge, and you remove the surcharge. The moment you remove the settlement occurs, you can remove the surcharge. So, you can monitor the settlements in the field and then remove the surcharge. So, the thing is, actually this is called this is what we need, this is you have to design for this particular time, which is very useful input into our own design, whole design process here. So, this is the same example, like you have a designed load, say for example some 100 kPa is acting. So, maybe you put 150 kPa or 200 kPa, depends, that also you should calculate how much of surcharge should be put. So, design load is something 100 kPa, you can put 150 kPa here. So, what happens is that this could be the thing, then remove that and then it comes back. So, the thing is the final settlements are always going to be like this, and it's an effective technique for accelerating consolidation settlements in clay soils. So, the principle is that, so like you must be able to calculate this is the load that you are expecting, this is the load plus the whatever is the stress that you are expecting from the building plus the fill total surcharge. So, this is higher, as I just mentioned, you need, like say for example, SC is a settlement under the load, SC plus SC is a load under the fill plus the primary compression. Actually, this is the primary compression. So, you can get within time T2 which is required here. So, to calculate this T2, we have a simple technique. We will see that we know that this is the proposed structural load. So, for example, I said 100 kPa, and the thickness of the clay layer undergoing consolidation is Hc. It can be a double drainage and single drainage conditions we know in soil mechanics. So, this is a standard expression that we have for calculation of settlements, like Cc into Hc by 1 plus E naught to log of this the stress caused due to additional load. One can use see this to calculate this stress, you have to use proper equations. There are analysis methods available to calculate the stress. So, you calculate this this stress at a particular point. What is the stress, extra stress because of the load, that you should be able to calculate from many of the elastic stress distribution theories, we have them. So, then this is the original overburden pressure. So, you know how to calculate settlement. So, now the other thing is that if you have the same whatever is extra load, you have higher load, that is it. So, when you have higher load, and of course, E naught is the initial void ratio of the sample or the void ratio at that particular depth. So, our objective is that the within settlement within this total settlement should occur within time T2, which is much shorter than T1, and then we apply some sort of temporary surcharge on the ground surface for the time T2. We will just keep. So, for example, how do you apply the temporary surcharge? You have sandbags and some of the material, I will show you, or whatever a weight heavy material, you can keep it, and then the settlement will be equal to SCP. So, at the time, if the surcharge is removed and a structure with a permanent load is built, no appreciable settlement will occur. So, this, as I said, they are all done by temporary fills. So, like this understanding can be obtained with reference to what is called the degree of consolidation at time T2. This is what we are interested. So, that is defined in terms of the settlement, the ratios of settlement at for the load P divided by the settlement at the load for the P plus F. So, like we have the expressions for both of them in the previous expressions we have seen, like we have seen these two expressions, and ratios of that, all other things get cancelled, and you have these terms. It is simple to understand. What we do is that these are the simple expressions. What we are trying to do is that you try to express in terms of the sigma naught here, and then this is one thing. So, you try to simplify this particular term. So, the degree of consolidation that you need at the point T2, you try to express in terms of the this is one ratio which will give you that this is one simple ratio, which is a extra load that you should apply in relation to its initial overburden pressure, and this is that load that you should apply in excess or as a ratio of the how much of fill load you have to apply. So, these two are the two ratios that are quite important. Like one ratio is nothing but it is a ratio in relation to the overburden pressure sigma naught. Sigma naught is nothing but gamma into H at any point. So, then how much of extra that ratio, how much of say for example, I just mentioned instead of 100 this is 100 kPa, this could be 200 kPa, some ratio one should have. So, actually one can the degree of consolidation you see is a function of these two variables. like the same variable is coming here also, you can see that this, then this is another variable. So, once you know these two coefficients, you can calculate the degree of consolidation at point T2. So, actually one can do a simple Excel plot, take the same equation and then plot. So, the degree of consolidation one can obtain here, like say for example, you can see that we need good degree of consolidation, right. Our objective is to get a very good degree of consolidation, and then this is the ratio which will give you the, so for example, this is the ratio of the delta P delta sigma with respect to the initial effective stress, and it can be 0.1, 0.5, 1, 2, 5, 10, it can be some numbers, like see initially it could be just maybe say 10 kPa, how much of extra you are putting, because that is additional load, and this is actually the other one, as I just mentioned, the ratio of the fill load is coming here. So, using this plot one can get this the information on T2, like you have to fix up, is it 6 months or 9 months or 1 year, you can fix it up, and by working out all these combinations you can get the number. I will just see an example. Then the degree of consolidation that we have is actually the degree of consolidation at time 2. What we do is that it is an average value, no, say you have about 10 meters depth, you are just at some point you are calculating the average value, everything is average. So, when you remove the surcharge and place the structural load, some portion of the clay close to the drainage surface will continue to swell, and the soil close to the midplane will continue to settle. So, what we do is that actually the degree of, in a clay embankment, the different points will have different degrees of consolidation. Like if for example, if they, so you will see that actually at the you must have seen in the theory that you have that lines of different degrees of consolidation like this, where you have both and both top and bottom there are open surfaces, free surface, the pore pressure is 0, right, pore pressure is 0, then at the midpoint the degree of consolidation will be little higher because it is away. So, that depends on the permeability of the soil. So, what we do is that the that particular thing, we assume that since this particular thing is there, removal of surcharge and the placement of structural load, what it does is that portion of the clay close to the drainage surface will continue to swell because you removed the load. So, there is some minor changes in the soil, and soil close to the midplane will continue to settle. So, to balance out, there is an approximate assumption that the whatever you have degree of consolidation is the mid plane degree of consolidation. We are just trying to average it out like this. So, this familiar thing we know, like we assume that the degree of consolidation is what you get is a mid plane consolidation, and we know this time factor, consolidation theory CV T2 by H square. CV is the coefficient of consolidation, T2 is a time, and maximum drainage path. So, we also know this particular plot, time factor versus degree of consolidation, which is a standard thing that we know in soil mechanics. So, knowing this, how do you solve the problem? It is a very interesting simple problem that I want to illustrate. You are trying to construct a highway bridge, and then the permanent load on the clay layer is expected to increase by 115 kilonewton per meter cube. You are getting some extra load, okay. There is some load, already there is some overburden at a midpoint, say for example, I said it is 10 meters. 10 meters is the thickness of the clay layer. So, at 5 meters the overburden pressure is 210 kilonewton per meter cube. How do you get that? Gamma by into H, right. So, this is square 210 kilonewton per meter square. So, then the CC and E naught void ratio, and it is even consolidation coefficient of consolidation also. Actually, we will try to put in terms of months, because what you do in the lab is just you try to calculate for seconds, but I want to for example 8 months and 10 months I am interested. So, I am putting everything in months. So, this soil is normally consolidated. Now, I would like to calculate the primary consolidation settlement of the bridge structure without pre-compression, and what is the surcharge required to eliminate the primary consolidation in 9 months by pre-compression. This is what I want to do. So, I just calculated in this particular steps what is the settlement? You can just see 415 mm, it is very high, about nearly 1.5 foot, right. Like you have all the CC, HC and 1.27, all that numbers are given. Then I would like to eliminate this by using the pre-compression technique. So, my objective is now T2 is 9 months and all these equations are given. So, TV I calculated, TV I calculated and I got 0.27. Okay. So, we have a figure 3 just we discussed for 0.27, the value of the degree of consolidation is 40%. So, with that in mind, what we have is that you have dP, this is already known, and the ratio of dP by d naught is this 0.458 you will get, and then there is a figure that I just showed you that for u like me which will give you the mid plane potential mid plane consolidation response, u for u equal to 40%, the ratio is 0.458, and you can work out that with all some things being known, the extra fill required is 287.5 kN per meter square. Actually, the thing is, in this case, in the soil, the soil I have purposefully taken that the soil is very loose or very poor soil. Actually, the soil liquid limit, the liquid limit is very high and all that, and with the result, you can see that it is 287 kPa is a high number. Normally, what they do in the field is that normally if the soil is somewhat, say for example, a lower type of lower liquid limit and all that, little like say for example, liquid limit is about 30% and all that, or 50%, one can really say that it may the load will not be this much, it may be about 100 or maybe 150 or something. So, how do you do this now preload? Now you got an amount of how much of preload should be applied, the delta sigma F you got 287.5 kN per meter square. So, how do you get it? For a simple example, I assume I have to fill. So, fill material I will take, it is about 20 kN per meter cube bulk density and 5 meters, it gives a preload of 100 kN per meter square. So, suppose I take sandbags which have this density of 20 and then load everything up to and load it up to 5 meters, and so density should be able to correct properly, say if it is 19, put 19. So, preload will be about 100, and then if I make it for leave it just for 9 months, then you have to monitor settlements also. So, it is we expect that the settlements will be sufficient, but normally what happens, see you are in a place where everything is clay, and to get a preload is very expensive, like even 1 meter, 2 meters, 3 meters is very expensive. Maybe normally people look for about 3 or 4, 5 meters, they can't go for like it becomes expensive. Imagine a place where everything is clay, it is a what is that, it is an island, it is full of clay, and you want to get sand, where do you get sand or where do you get weights, it is very difficult. So, it becomes very expensive. So, what we do is that in this particular normally we can, that is the reason why we are trying to increase this degree of consolidation by other means. In this case, what is happening, it is only the vertical consolidation that is occurring. Now, we try to use the sand drains or PVDs, and let us see what is going to happen. This can be worked out, it is a simple thing. So, required surcharge is higher than the preload, and hence consolidation by sand drains or PVDs is required. So, we will see, and so this is a typical preload, how it looks like, it is so difficult, you see, like it is quite difficult, like you may just dump it, maybe this is about 5 to 6 meters or 7 meters, like you have to make some arrangements, and how are you sure that the preload is effective? There are a number of issues, but still it is a technique that has been quite useful, and people have used it for many years, like before 1970s and 60s, this is a technique that people used. So, what is that advantage? You can see here, like you have a preload, you have the this is extra the whatever is the surcharge you are trying to place, its consolidation is only vertical, slow draining subsoil, because the consolidation of the soil is less. So, that is a problem, but here because of the provision of the drains like this, as I just mentioned, like this, if you have drains at every proper spacing and all that, you can see that there is a consolidation occurring here because of that, like all the drains, so that is the reason why it is going to be very effective. So, these are the, as I said, it is a filter jacket, you have a plastic core, and these things act as the drainage channels. Actually the advantage is that, see the I must tell you the difference. Sand is one thing that you normally you can use the same thing for sand drains. Okay, sand drains you will get it, and the advantage of the sand drains, yes, is that if they are cheaper and economically viable, it is alright, but the problem is that over a period of time the clay and sand gets mixed up, and there will be a problem, between the soil and sand and clay. There will be some place where the permeability is again a poor, some sand will not be, sand column will not be complete sand drain, it will be some other extra, like some area gets smudged, or what we call it smear zone, and that is the permeability of the smear zone is very important. And the advantage is that, like if you have radial consolidation, you can see the difference here. See, you can see that with time, and then this is settlement axis, and with vertical drains, this is without drains, this is the degree of consolidation. Drains without surcharge is one thing, drains with surcharge and removal of, you can see that within this construction period, you specify that some time, all consolidation is complete, whatever settlements over. So this is a very ideal technique for accelerating consolidation. So as I just mentioned, the purpose of the ground import technique is very important. In this case, we are looking at accelerating consolidation as the main purpose. And say for example, if I say that the sand can also work as stone column type of thing, we call it sand compaction piles, but the difference is that here it is a drainage is the main thing. In the sand compaction piles, it is a bearing capacity that is more important. So one should not mix up both the issues, and one should clearly understand the purpose for which it is designed. Here it is being used because it is a radial consolidation has been quite useful in increasing the rate of consolidation. So as I just mentioned, the radius of sand drains or the sand drains or the derivatives such as sand wicks, or these are all its derivatives, whether it is a this is a coir one, this is a jute one, they can be all very we say that sand drains are circular in cross section, like we just said 10 centimeters of the drain will use it, but for the prefabricated drains, because this is actually easy to install. Why this is in the shape, the thing is that the shape is very important here, that sand drains, actually we make a bore and then put the sand and all that. Here we make a, we will just see that technique where you install this thing and then put in, there is an installation technique specific one here, and because to suit that we should come up with the shape. And so for prefabricated drains, the situation is different in the sense that it cannot be circular, and actually the band shape of the prefabricated drains, the flow pattern around the drain is considerably altered from the cylindrical case. Therefore an equivalent drain radius ought to be calculated. Actually we have a standard diameter in the circular one, but here we try to use an expression like this: equivalent diameter is 2 into b plus t by pi. This is what we use, where b is the width of the strip, this is the width of the strip, then this is the thickness of the strip. So you get equivalent diameter. So there are some, so just to get an idea what is this, you can see that it is about maybe 900 mm or something like that, and these are all different sizes, you can see that. So you can see that one of the Gelman is something, one of the popular persons who did lot of work in vertical drains, and in fact they were using, inside one is called core, the outer one is called filter, they were using cardboard papers as for drainage, and the dimensions were 100 mm into 3 mm. Then PVC one case, geodrains another example, PE is a polyethylene, cellulose, and coal blond is another for some company which has a polyester inside, so for example this inside one core is a polyester, the outside is polypropylene, like that. So essentially the size is something very important, this is very crucial. So the pre-consolidation of soil in a vertical direction is very in the preloading, it is only the vertical one that is effective, but since in the case of the PVDs and sand drains, you have the radial consolidation also, what happens is that it results in lesser preload. Like as I just mentioned, I cannot get all the, our objective in this case was to increase the rate of consolidation, and in the case of preload, it was requiring very huge amount of preload to be applied on the sample. But here what we are doing is that we are able to have a good combination and come up with radial consolidation in addition to vertical consolidation, significantly increasing the consolidation rates. As I just mentioned, the sand drains were used since 1930s, and prefabricated vertical drains in the form of cardboard wicks were also used initially up to 1950s and 60s. Now prefabricated vertical drains are being used. Actually this is quite effective, and in addition there are so many advances in this area that see, like one way of doing applying load is that you apply some load, you can also apply vacuum. What you are doing is that you are removing water, by loading clay soil, what are you doing is that you are trying to remove the water or reduce the water content. So instead of that, you can as well apply some suction, so for example we are used to removing from in the specific gravity test, we are used to vacuum pump, So you try to remove all the air, all the water and whatever is present. So you try to create a vacuum which can really suck all the water. So that is one thing that we will see again, and so this is another major advantage in the recent times. We will see some of that. So how do you go about calculations? That is very important. So to increase the degree of consolidation using sand drains or PVDs, average degree of consolidation due to drainage is, like now you say that UVR. UVR is nothing but 1 minus, so 1 minus UR into 1 minus V. So both radial and vertical consolidation, the degrees of consolidation are used, and how do you calculate them is what we will see now. So average degree of consolidation due to radial direction only, okay. This is an expression which is derived, okay, and so this term M is given in terms of M is n square minus n square divided by n square minus s square. S is the spacing of the drains. So this is an expression which will have the permeability of the sand drains. Actually these two are the permeabilities in the of the soil in the horizontal direction, and then the permeability in the smear zone. As I just mentioned that between the two, like you have a sand drain, then you have a clay here, next to that some amount of material is, we call it smear zone, and the permeability is little low there, immediately after the clay surface, I mean immediately after the sand, from sand it should come to, from the drainage medium it should come to clay. The permeability needs to change drastically, but it is not so, but there is some area where there is a low pocket of clay where there is a less permeability. So we need to calculate the drain spacing, which is nothing but RE by RW, like it is nothing but RE is the equivalent radius of the configuration, because we assume that each drain has an influencing area around it, and then the radius of that is RE, and then the RW is the radius of the drain, okay. So and then as I just mentioned, KH and KR are the permeabilities, and then once you know this, say for example we calculated the CVR, right, yeah. So you have to calculate essentially the time factors. So you know there is coefficient of consolidation for radial drainage, and you calculate changes in void ratio and all these factors, and once you know this radial consolidation coefficient, then our problem is solved. Essentially what we are doing is that, and for no smear case RS equal to RW and KH equal to KR and S equal to 1, and so whatever is the earlier equation, it is somewhat simpler, and this is for radial consolidation. So, next one is the you have a similar equation for the vertical consolidation, which we know from the theory itself, from the soil mechanics theory, like TV by that for degree of consolidation between 0 to 61 equation, we have those things. So, use those equations and go ahead with design, and then use the expression in this, like yeah, in these expressions. So, ER is to be calculated, and UV we know from fundamentals of soil mechanics, that vertical consolidation theory we know. So, using the time factor and all that, one can calculate. So, you substitute that, there will be a big difference. So, this is the one that causes major difference, and so this vertical consolidation is known. This is what you have to calculate. This is a function of the, as you just saw, the permeability of the soil, permeability of the I mean the diameter as also plays a role, like as you just saw, like number of sand drains, how many sand drains you have to put finally, all that. So, all these things are important, and once you know that, you calculate that, and then use that regular equations, like one can get a simple degree of consolidation with drains, without drains, and if the horizontal permeability is equal to vertical permeability, what happens? Normally horizontal permeability will be higher than the vertical permeability. So, that also you can calculate. In fact, we have made some calculations, I will show you later, where it is also a very significant variable, because many of the soils are stratified in nature, and we can't take vertical permeability equal to horizontal permeability, always the horizontal permeability is higher. So, once you put in that particular thing, and then one can develop some sort of equations where the degree of consolidation without drains is about very, I mean could be very slow, but with PVDs taking vertical and horizontal permeability same, there will be a very good difference. But if you really take the permeability in the horizontal direction as higher than the vertical one, you get a very good difference. So, you may just see that it is very effective, maybe as I said, within 9 months or 6 months, whatever you want, one can design the spacing and all that, and then complete the project. That is a beauty here. So, it is very simple technique, and one can effectively use that, and we will see some how it can be done in the field and all that. So, essentially as just mentioned, the rate of consolidation and the settlement is controlled how rapidly the pore pressure can escape from the soil. So, the spacing and the permeability of the soil are the important variables, okay. And so, one can actually, what we do is that we develop a set of design curves of drain spacing, fill height, and consolidation time. The thing is, like see, that there are 3 or 4 variables here. Your degree of the thing is, you also have the preload is there, preload is there, but if you want to minimize the preload, like you have to see the what spacing you should provide. So, is the spacing if you provide a wider spacing, the probability is that the preload will be higher, but then if you want to reduce the preload, then you need to come back to a closer spacing something, and then the permeability also, of course you can't change the permeabilities in both horizontal and vertical direction should be measured in the field, okay. Laboratory tests will give you some information, but then field permeability results are going to be very accurate, because you cannot make an error in these cases, because everything depends on the permeability of the in situ soil, right. So, you need to develop a set of design curves, like it is a parametric study one can do, addressing what should be the fill height, consolidation time, and the spacing and all that, and you will get reasonably, like you have specified, say for example, instead of 6 months you want to say 1 year, you can say that. So, the thing is, like it depends on your requirement. If you can allow for 1 year, it is different, 9 months it can be different. So, you can do a parametric study of all these factors and fix up a particular most appropriate thing, like for example, the fill quantities that you want as preload, you may be limited. So, you need to consider that is an important variable, because it is going to be very expensive in a project to get a preload from different places, when it's when you need to say 5 to 10 meters if you want to construct it, is not possible. So, you would like to reduce it to a maximum extent and see that there is an optimum combination of all these factors, and it is going to be cost effective. I would like to just highlight some advantages of the prefabricated vertical drains over sand drains. In fact, sand drains have been effective, but the fact is that these are all sand drains have a sort of, you have to make a bore and then they put the sand material, whereas some of these materials have to be mission with using missions you have to do that. So, in fact 5000 meters per day can be done. It is a very fast, like one can do very fast, like like what you should do is that it just say 10 meters is the depth of soil to be improved. So, it just there is a mission that takes it down, there is a this thing they, like it does, you can't, then there is a, you have to cut it and then there is a drain that gets established. So, the advantage is that they are very fast, that is one number. There is no risk of PVDs breaking insulation, while sand drains may have discontinuities if the mandrel is withdrawn too fast. Like if you remove that particular mandrel, the problem is that the these are all somewhat stronger material. In fact, whereas the sand material fails by shear, shear strength and all, those things are somewhat important, and they may have discontinuities also in the process of doing that. So, it may not be as good as compared to this, like it is number one, the reason is that the shear failure of the PVDs is during the settlement is less, whereas sand drains are vulnerable to shear failure during settlement, like there could be some movements and all that, it is not easy for in terms of the quality control. The other important thing is the PVDs have discharge capacities which are very high, like you just said. Actually, the beauty here is that, as I just mentioned, this filter allows only water, all the clay is outside. So, it is then only water goes inside. So, it is an excellent filter cloth, and the inside is what is an the excellent drainage cloth, and all the water will come up, it gets pumped up, and it is either it goes down or something, you have either it is all by gravity, anyhow water is released because it is open to atmosphere and then water comes out. So, you can see that the drainage capacities are quite like so for example 30 to 90 here, whereas the discharge capacity with a say 35 centimeters diameter sand drain has a discharge capacity of 20 into 10 power of minus 6 meter cube per second. How much of water? Okay. So, this is here you can see it is more 30 to 90, about much higher. Okay. So, when installed with a properly designed mandrel, smear effects are much less for PVDs than for large diameter sand drains. As I just mentioned, the sand drains have a smear effects. So, the zone of smear is directly proportional to the diameter of the mandrel used for installation. So, PVDs are factory produced materials and are quality controlled, whereas sand drains are subject to the quality variance of naturally occurring sands. We know that the sand occurs natural, it is a natural material, there could be problems of gradation and all that, it is not easy to get, but whereas like it is quite simple. The thing is, the purpose that you want to have from sand is a good drainage, but if that depends on the gradation characteristics of the sand, its availability, its time effects, there are so many issues there. Of course, the time is short here, like you would like to have it is about 9 months, but the fact is that they are all processed materials, that is a very good advantage. So, that is the reason why, because of its ease with which it can be done, like easy fabrication, easy quality control, economy and small disturbance on soil during installation. These techniques are particularly using PVDs are used in a significant way. As I just mentioned, the vertical drains can be in some spacing, either a triangular or square, similar to stone columns. Consolidation problem is simplified to an axis symmetric one. Say for example, there is a Barron's theory of radial consolidation, one should read that. Okay. There is a Barron's theory of radial consolidation, which is, we know Terzaghi is the one dimensional consolidation, which is vertical. So, you need to read these Barron's papers and some more additional papers we have, which like it is a very classical work. So, we use that particular thing and we assume that you have a material here and then it has a effective drainage area, you have an effective drainage area, that is what we call it. So, an equivalent radius of the soil cylinder based on this same total area for different installation patterns is used, like say for example, installation is also an important variable here. Okay. So, this is a square pattern is one way, like you have 4 sand drains here and the triangular is also one thing, like it can be a hexagonal type. This is one important thing. Very important thing is that when you are trying to construct the preloading and all these equipment, I mean, or even the sand drains or even the prefabricated vertical drains, one should really do some sort of trials in the field. How do you do the trials in the field? Actually, this is a very popular concept in west in the sense, particularly in Netherlands, and say for example, if you go to Scandinavian countries like Denmark, Finland and all that, the soil is so soft, many of the techniques will not work. The maximum ground movement techniques were done in those areas in 60s and 70s, and even now it is an exciting area for geotechnical engineering. If somebody has a chance, it is an exciting area to be in that countries, Scandinavia, Denmark, Netherlands, all those, Finland, where lot of geotechnical activity is going on, and they have done lot of work, quality work, and then they have been trendsetters for the rest of the world. And then they say, because we know that, say we try to work on the properties that are you obtain from the lab or from the field, and then you are trying to assess the performance of the embankment. Best way is to construct an embankment itself, like 5 meters height or 3 meters height or whatever height you want. And the advantage is that if you have that type of thing, it avoids the uncertainties that you have with reference to sampling, then other difficulties like installation. Then the other advantage is that you should be able to, if at all you have decided about constructing a trial embankment, you must be able to make it, say for example, if you are trying to construct a 5 meter embankment connecting 2 villages. So, for example, villages are 20 kilometers apart, you need a highway embankment between the 2 villages, and then the height of the embankment is about 5 meters, and the slopes, everything is known. So, that vertical you can as well construct about say for example 100 meters or 50 meters trial embankment, and then do all the experiment before you really take up the work. Then once you understand everything from that, then that can be used as the input for improving the rest of the work. That is the thing that we are trying to do here. So, it needs to reproduce stress and field conditions that are representative of the actual structure, so that you can use whatever information and you get from that in a proper way, and better that it is a part of the final structure. Say for example, if the alignment is between 2 villages connecting them by for a distance of about 20 kilometers, that particular thing, whatever, say for example 50 meters could be a trial embankment. In fact, I had opportunities to see many trial embankments in Bangkok. In fact, the Bangkok soft soil is so bad that they did, particularly Asian Institute of Technology, they did so much of work on soft soils, like they have particularly from Professor Bergado. There are many people working in the area, and then even in Singapore, Professor many like even Singapore soil is also very soft and very tricky, clay problems are always tricky. So, they did lot of work using some of the concepts, and they say that it should be the part of the final structure. And actually the thing is, okay, you have to measure the performance of the trial embankment. How do you do measuring? You have to measure pore pressures, you have to do settlement gauges, you have to have leveling points, all that. Essentially why are you doing is that our objective is to reduce the settlements. You can see here one simple example. Okay, see the thing is, see there is a water table here. Most of the time there is always a problem, like you are trying to, soil is water is there existing, you are supposed to construct. Sometimes under the water also you should construct. How do you do this? So, this is all soft soil here. Okay. Then you have an embankment here, which is supposed to be a proposed embankment. You can put a surcharge like this here. Okay. You can put a surcharge here. So, this is a drainage blanket, which we normally, because see these are all PVDS or sand drains. The thing is that this the sand drains, as I just mentioned, when the water comes out, the effective stress, like they are open to atmosphere, so there is no pressure there. So, that is how it is, and this all that, and here you see that this is called settlement platforms. You have to see how is a whole embankment settling. You have 1, 2, 3 settlement platforms, that have been installed in the, you can clearly see that they are installed in the drainage blanket, we call it. It is very clear, and then this is on either side of the center line, it is very clear. You have these sort of settlement gauges clearly. Then piezometers. So, you are only trying to measure on one side of the this thing, because this side is this is actually uniform area. You can see that the area is quite uniform. You put piezometers here. Piezometer means they measure pore pressures, because you are applying load, and when you apply load, see, the thing is, before construction of this embankment there is no pore pressure, is it not? So, there is no pore pressure, like you are trying to measure pore pressure here, pore pressure here, pore pressure here, there are 4 points here. So, you are trying to construct pore pressures. So, what we do is that these pore pressure are continuously measured, okay, whatever, some frequency of intervals could be there, and once you measure the pore pressures and settlement gauges, you will be much more comfortable. Okay. So, that is a very important concept here, that the instrumentation is a very vital component, particularly in soft soils, and so much of work was done on these lines, and they use you are applying some stress, you are applying, then you are trying to measure pore pressures, you are trying to measure settlements. So, it is like constitutive modeling has been very powerful tool to understand all of this, like suppose there is an extra load applied, how much of pore pressures are mobilized, how much of settlement occurred. So, that is what one can do here. Say, like they keep on constructing, see, once you the way we start is that this is a pore pressure, this is settlement gauge. The moment you put some layer of, say, for example, 1 meter of embankment, then there will be pore pressures mobilized and settlements induced. So, measure the settlements and pore pressures, put one more layer of compaction or the sand, this all embankment, keep on putting it and putting this, even put the, what is that, surcharge also. So, monitor for at least 1 year, 2 years, at least 1 year, then because it is one full season, it will give a good information. Okay. So, this is how we do that, and this is a typical construction. In fact, you can see that sand is coming here, and being, this is what it is going under the paddy field. In fact, this is what I mean, I was seeing in a typical Kerala also, where you have a lot of paddy fields, and then between 2 villages you try to construct a road, and then you have to destroy all the paddy fields and then go ahead with construction. So, I was wondering, is the development costs, the cost of development, is it leads to reduction in the food grains consumption in the area. So, how do you do that? Actually, we have to have a rig here. You have to position the rig at the drain location, place the anchor on the drain end, penetrate the mandrel to the desired depth, withdraw the mandrel, cut the drain material above the drainage blanket. This is what we do. So, this is the type we have, like this is all, like as I just mentioned, this all comes in rolls, about the cost maybe per meter, some numbers like $2 or whatever, some in fact 30 rupees for including the cost of installation also. I mean, there are some different rates one needs to work out with in consultation with some of the suppliers. You have suppliers also, you have installers also, you have full time persons taking everything. So, this is that particular drain, this is done in the field. You can see that this is that mandrel, like this is the one, that first one, then you insert it into the soil, you cut it here, leave it here, just like this, then put your sand blanket or whatever. Okay. So, the advantages are that it leads to increased shear strength of the clay, it enables the load to be applied more rapidly, thus better use of the construction plants. In the case of embankments and steeper slopes, and provision of berms could be avoided. Sometimes these are some of the standard techniques, provision of berms to improve the stability and all that is normally done. Lower amount of fill is required, as I just mentioned. It greatly helps in reducing the amount of preload required, increased rate of consolidation, and it saves a lot in the construction. Then increased rate of consolidation, reduction time required for primary settlement, structural embankments can put into commission and use far earlier, reduction in the cost of maintenance. In fact, that is one of the other things. Stability to embankments, many soft clay strata contain thin band or parting of sand or silt. In fact, in some places like in some places where you have alternate layers of, you have a clay and then you have a sandy material. So, there will be some pore pressures developed and all that. If you have a drainage system like that, it will release all these excessive pore pressures. That is a very important thing. So, this have applications of PVDs have been too many, like people have been able to use in airports, golf courses, dredge consolidation, mine tailings, tailing ponds, swamp areas and wetland development, building foundations, retaining walls. I mean, in fact, it can be even used for drainage purpose also, parking lots, landfills. Now, wherever there is a possibility of increasing the acceleration of drainage or the consolidation response, these have been quite effective. So, nowadays, of course, these are all about installation techniques, where it can be done with modern approved equipment such that there is a minimum disturbance to soil, so that subsoil, so that it does not lead to the permeability being low here. At this stage I will stop and we will continue it further. Thank you.